Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on special functions. And before jumping to another function, I want to talk about a little bit about this number, Euler-Mascheroni number. And you've seen in the previous lectures that when we talk about the gamma function and the factorials, this Euler-Mascheroni number pops up everywhere, even in the digamma. Anything related to the gamma function, this Euler-Mascheroni number pops up. So it's good to just we take a moment and just look at it and see what it is. So gamma, this number, is the limit of a simple sequence. So you sum from 1 to n the numbers 1 over k, and then subtract minus log of n. And this is a sequence, right? N is the parameter, and you sum from 1 to n. And then this sequence must converge, and you can just easily justify why it must converge. To give you some ideas, so all the terms of this sequence are positive, all right? A1, if you call this sequence AN, A1 is positive, and A1 is 1, right? Because minus log of 1 is basically 0, and sum from 1 to 1 of 1 over k is 1. And then A1 is positive, A2 is positive, and you can prove that all the terms are positive. And this sequence is monotonically decreasing. It always is monotonically decreasing. What it means is that an plus 1 for any n is always less than an, all right? So all the terms are positive, the sequence is monotonically decreasing, and obviously it has a lower bound, which is 0, because all the terms are always positive. And any sequence that is monotonically decreasing and has a lower bound, it must converge. So in 1730 or 1750 something, when Euler wrote down this sequence, he already knew that this is going to converge. So he tried to find this number gamma, and he called it, I think it was called after Euler. So here I have it. I just took the value from Wikipedia, and it has about 25-30 decimal places of accuracy: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It has 20 decimal places of accuracy. There are a couple of things very interesting. First of all, if you sum only 1 over k from 1 to n and let n goes to infinity, this part diverges. When n goes to infinity, this part diverges. So 1 over k, the sum of 1 over k always diverges. And these actually have a number, this part of the sequence from 1 to n, 1 over k. This sum has a name which is called harmonic number, and typically is denoted by h sub n. So h sub n is sum from 1 to n of 1 over k, and it diverges. When we subtract this log, it's very interesting. It is able to tame the divergence and make the whole sum converge. And then if we want to look at the error behavior, because obviously it's very slow, so any reasonable person is not going to just sum it up. And definitely Euler, when in 1780 something, when he was summing this up, he didn't just sum the term up, because the convergence is very slow. And obviously he didn't have a calculator or a computer or anything. So if you try to analyze this the behavior of the error, you end up with the fact that the error has a behavior of 1 over n squared. It's not bad, but it's not the greatest. What we want is like 1 over n to the 4th power, n to the 5th, n to the 6th, so very fast convergence. This is relatively slow. But the behavior of the error is 1 over n squared, and again, it's not oscillatory. The sequence is monotonically behaving, decreasing, so it's perfect for Richardson acceleration, and that's what I'm going to show you here, all right? So what I'm going to do, what we do is, in order to find the limit of the sequence, I create a sequence, and again, we're using our wonderful implementation of the sequence, which was a functional interface with a bunch of default functions, which add more capabilities to a functional interface in Java. So I try to sum this up, so k from 1 to n, 1 over k, and then subtract the log of n from it. This is a natural log. And then I create another sequence R4, Richardson 4th order, right? And then do the Richardson 4th order transformation. And if you recall, this is a default method and returns another functional interface sequence. And then we calculate this fourth order Richardson and evaluate it at 20. Very small number, all right? But then I go and create my index. I want to sum for different ends from 1 to 1000. I want to calculate the original sequence, and then I want to also calculate the fourth order Richardson version of it. And then I plot it, of course. Now what you see is that this blue one is the original sequence, and I wasn't kidding when I said it's a painfully slow convergence. So if you want to like 10 decimal places of accuracy, you have to sum like 200, 300 terms. But when we do a fourth order Richardson, suddenly it becomes extremely fast convergence, even with 20 terms. When I say 20, I mean we have to sum only 20 terms. I mean, it's not exactly 20 terms, but because when we do Richardson fourth order, we evaluate at n plus 1, 2, 3, and 4. So at max, we need to evaluate 25 terms of this sum, right? Which is not that much. So let's head to Eclipse and try to actually look at the result. So in our special function package, I have this let's see if I test Euler-Mascheroni, right? So I create my sequence here, and then I accelerate with Richardson fourth order, and then evaluate both sequences and then plot them. So let's run this, see what happens. All right. I mean, it's very obvious what's going on, right? Beautiful this convergence is so good, right? After 10 terms, we're pretty much there. You cannot argue that after 10 terms, we have extremely good. So this makes finding the limit of a relatively painfully slow convergence very easily, all right? And let's see what I found. If I sum 20 terms with the fourth order Richardson, I get 577, 215, 66, 4, 7. All right. So 3, 4, 5, 6, 7, 8, 3, 6, 9 decimal places of accuracy. 577, 215, 664. All right. 9 decimal places of accuracy with only summing maximum 25 terms, right? So what I want you to remember is that in 1780, when Euler was around, he didn't sum like 1000 terms to find this limit, right? He actually got it with 8 to 9 decimal places of accuracy, but he was definitely very well aware of the behavior of the error and the Richardson acceleration. So whenever we try to sum sequences, we don't sum them up because most of the sequences, they just have a very slow convergence. So we analyze the behavior of the error and then choose an appropriate acceleration transformation, okay? So this is very important. If you are not comfortable with these ideas, then go back and review my lectures on sequences and series and the sequence transformations, all right? All right, let's move on. So again, back to our gamma function. So far we have looked at the digamma function. There is another function that is generalizing the concept of factorial. Actually, it's called the beta function, which is b of x and y. It takes 2 arguments or 2 parameters, and it doesn't generalize the factorial itself. It generalizes the idea of the combinatory function. We know that the combinatory function c, n and m, right, is c n plus m, for example, is or 1 over this 1 over c n plus m, let's see, n from m plus, so the combination of n from m plus n terms is m plus n factorial over n factorial m factorial, and this beta function is basically 1 over this. So gamma represents the factorial. So this is like x minus 1 factorial, 1 minus 1 factorial over x plus y minus 1 factorial. All right. So this is related to this combinatory function when we deal with integers. Now this is true for all x and y, even when we extend the x and y to complex numbers. But beta function has an integral representation for real of x positive and real y positive, which is t to the x minus 1, 1 minus t to the y minus 1. All right? And we do not need to go and try to implement the beta function using the power series. We can if we want to, but our implementation of gamma function was fast enough, so I'm just calling our gamma function gamma of x, gamma of y divided by gamma of x plus y. And this works both for real numbers, double xy, and complex numbers. All right? And this beta function has some very interesting properties. First of all, x and y, you can exchange the position. So beta of x and y is equal beta of y and x. This is just by definition, right? This multiplication and this summation. But beta of x and y, you can write it as beta x and y plus 1 plus beta of x plus y and x plus 1 and y. And this comes from the main property of the gamma function. So gamma function was defined based on the property that gamma of z plus 1 is z gamma z, with gamma 1 is 1. Any function that behaves like this is the gamma function. So back to our beta function. So if you look at beta of x and y plus 1 is gamma x, gamma y plus 1 over gamma of x plus y plus 1. So gamma y plus 1 is just y plus 1 is just y times gamma y. And gamma of x plus y is basically x plus y plus 1 is x plus y times gamma of x plus y. So this, you can prove this, but this fact, this identity actually comes from the next two ones. So beta of x plus 1 and y is beta of x and y times x over x plus y. That's because gamma of x plus 1 in the numerator is just x times gamma of x, and gamma of x plus y plus 1 in the denominator is just x plus y times gamma of x plus y. So beta of x and y comes out, there is an x over x plus y. And again, we can always change the x and y. So beta of x and y plus 1 is beta of y and x over y times y over x plus y. And we know that beta of x and y is equal to beta of y and x. So we get this. And if you sum these two up, which is the right hand side of this, x over x plus y plus y over x plus y is 1. So we get this identity. Now the next one is beta of x and y times beta of x plus y 1 minus y is pi over x sine of pi y. And finally, we have a reflection formula. Beta of x and 1 minus x is pi over sine of pi x. And these two just directly come from the Euler's reflection identity for a gamma function. So Euler's reflection formula, obviously for non-integer z, because there is a sine of pi z. So gamma of 1 minus z times gamma z is pi over sine of pi z. And if we go back to beta, beta of x and 1 minus x is gamma x, gamma 1 minus x, which already gives us pi over sine of pi x, times divided by gamma of x plus 1 minus x, which is gamma of 1, which by definition of the gamma function, it's 1. So we get this directly from Euler's formula. And you can also prove the other one. But another interesting property here, for example, beta of 1 and x or 1 and y. So if I set, for example, x to 1, then beta of 1 and y is gamma 1, which by definition is 1, times gamma y divided by gamma of 1 plus y, which by definition is y times gamma y. And gamma y cancels out. This becomes 1 over y or 1 over x, all right? So beta of 1 and x or beta of x and 1 is 1 over x. And as you can see, I have plotted. And at 1, we get 1. At 2, we get 1 over 2. At 3, we get 1 over 3, etc. All right? So let's head to Eclipse. I have this beta function here. And we're just creating a gamma function instance. In the constructor, we created, and then we just use the definition. There are other functions related to the beta, such as beta ln, beta log, which is log of absolute value of beta. And for complex, we can also define beta and beta log. All right. And I have also created a beta function, test beta function. And in test 1, I'm plotting from point 8 to 5. And I'm calculating, let's say, 1 over beta of x equals 1 and y is changing. So let's plot this. Okay, we are getting some errors. Why are we getting some errors? In the beta class, let's see. I believe it has to do with these complex numbers. So let's keep this. Let's remove this and run this again. It's pretty fast, 84, and we are getting our 1 over x, right? So whenever we have beta of 1 and x, it becomes 1 over x, all right? And we can export this to Python and compare it with the Python implementation. So if I open the text file and copy all these numbers and go to our notebook, I'm going to paste this and x0, y0, and from scipy package, scipy.special, I will call the beta function, beta, all right? Now remember, we plotted 1 and x, so the first variable is fixed at 1, the second variable is our variable x, and you see we get a perfect fit, all right? Now for complex numbers, so if we just want to evaluate beta at complex numbers, then I'm going to run test 2 here. Let's see. So beta at 1 plus j and 2 minus j is, let me also do a sysout on u itself. And 1360 minus 1360, and as you can see, we get the 1 plus j and 2 minus j, all right? Okay, I hope you enjoyed this lecture, and I'll see you in the next one.